I bid for this conference a few years ago, and we had to fight all sorts of national manipulations to try to get the conference somewhere else, and it was an extraordinary opportunity to have this conference here, and it's really nice to be able to speak to all of you. So, fire or temperature? I mean, I think this is really the question that I would like to address, and how does that affect structural analysis, and what are the things that we need to consider? I think that if you look at journals like Engineering Structures and so forth, you will find that in the last decade or so, there's been an enormous increase in the amount of people that have been working in this space. Many papers get published now in structural fire engineering, and unfortunately, I believe that many of those papers end up missing some very fundamental aspects of the problem. And the reason is actually quite simple. It is the fact that fire engineering or structural fire engineering is at the convergence of two disciplines that have been very separate for a very long period of time. And I wouldn't be afraid of asking most of you that were educated as structural engineers is if you ever were required to take a heat transfer or a combustion class, and most likely the answer from the majority will be no. So the fact that there is a real lack of knowledge on very fundamental aspects of structural behavior in fire leads to many times very significant misunderstandings. Needless to say, also fire is quite unusual in the sense that it doesn't work like most other loads. And I'm going to try to make a case of why that is the case. So the traditional approach that people have towards the design of structures seems to somehow fall to pieces when you start looking at the behavior of structures in fire. Now, most of the things tend to remain unidentified, and we keep following the same routine in a constant way, trying to deliver always the same type of analysis, without recognizing that many times the devil is in the details, and we're missing some of the very critical details. So I'm going to try to highlight a few of those details in this presentation. So the first thing is where we start, and what are we moving away from, and where is the motivation to move away from this? So in principle, you would imagine that if you were to design a structure, you would like to have an explicit representation of the behavior of that structure. A structural engineer, when they design a structural system, they will start looking at quantitative terms like utilization, safety factors, and so forth. This has not been historically the case in any aspect of fire engineering. So fire engineering always relies on the basis of implicit performance. Now, why do they rely on the basis of implicit performance? Because we live around the concept of an adequate level of safety, where adequate never is defined. If you have to define what adequate is, you have to start by defining what is the cost of life. And because we refuse as a society to assign a cost to human beings, we refuse to assign a cost to life safety. And therefore, staying with implicit performance has been the norm for more than 200 years. So if you think about it, that applies to every aspect of fire safety engineering. And if I look at the problem of fire safety, what we find is that we have these solutions of implicit performance that are basically one size fits all. So it's something that is deemed to be adequate. So if you're talking about a travel distance, you would say if it's less than 30 meters, it's okay. If it's more than 30 meters, it's not. So because of that, we standardize space. So we are responsible for effectively ruining architecture. We have completely standardized space where effectively all corridors look the same, because we derive all the dimensions of corridors on the basis of fire safety specifications. We devise concepts like compartmentations, where we put limiting sizes to all compartments, because that's a fire that a firefighter can fight. We basically define the characteristics of ceilings, for example, so that our sprinklers can work. So odd shapes in ceilings are not possible. They have to be flat, because otherwise the sprinklers don't work. And we put these oddities of these like sprinkler heads in all the ceilings. So if an architect wants a very smooth ceiling, that cannot be done. So if you have a concrete slab that you want to expose, you will have a very nice red pipe underneath with the sprinklers coming out. And that has to be there. So the sprinklers are clearly an aspect of it. In a similar way, we specify passive fire protection as the only means to try to protect the structure from fire, which effectively means that every structure has to be covered. There's a very, very famous case. It was Mies van der Rohe when he designed the Seagram building, and he wanted to expose all the steel columns, and he was told by the codes that they had to be fireproofed. So basically they fireproofed the steel columns, but because he still wanted that image, he covered the fireproofing with brass elements that resemble the steel columns. Now, nowadays, those brass components keep falling off, so the maintenance cost of that building is absolutely extraordinary. And there's a very important phrase of Mies van der Rohe when he was interviewed, and he was describing how the fire protection engineers ruined his design. He said that every time he looked at that building, he felt like crying. We really don't want to do that, but we do it on a regular basis. We make architects cry. So, and in a similar way, we have standardized a fire service that if we analyze situations like Grenfell, we realize that those standard practices, when exposed to a situation that is abnormal, the result is that you get an absolute disaster. So all these things at the end, brings us to a combination of two things. First, enormous factors of safety, because we're operating on a one-size-fits-all scheme. So if you want to estimate purely from an energy balance what is the safety factor of a sprinkler system, it is about 10,000. Now, tell me any other engineering system that operates with a 10,000 safety factor. There's none. And so we have enormous factors of safety, so society has recognized that there's a lot of potential savings that can be doing fire, but that requires start looking at the problem from an explicit performance manner. So you cannot rely on implicit performance, because that immediately brings you back to these very extensive safety factors. Now, one of the problems that this approach has is that, as I said, you lose many positive aspects of design. So for example, you lose function. So for example, that image of that stair represents a stair that is there by code because it is required. Nevertheless, because it is external, it is a stair that probably will never be used, even in the event of an emergency. So we're putting a functional element into the building that has no function, just because the code requires it. In a similar manner, an architect wants to have, for example, an opening in 2 floors, and they want to expose a monumental stair. Well, we box it. Why? Because we cannot allow openings between floors, because fires cannot propagate beyond 1 floor. So all these things, happen. We compromise aesthetics and all these things, but nevertheless, at the end, there's negative aspects of it. One of it is that we have enormous amounts of waste because our safety factors are enormous. And this is an example in that figure of the deployment of fire protection foams. Fire protection foams are halogens that are high contaminants. Nevertheless, we deploy them in quantities that are extraordinary. And today we have all sorts of litigations, for example, in Australia, regarding the contamination of soil by PFAS, which is a product of fire protection foams. In a similar manner, there's a lot of unidentified mistakes. And things that we think we're doing right, eventually we don't. Now, let me show you a few images so you can see how random the methodologies that we have when it comes to the design of structures in fire are. So effectively, if you talk, for example, about tall buildings, above 30 meters in some countries, above 18 meters in other countries, it depends where you are, you have a certain set of rules that you're going to be applying to try to design those structures that in principle will imply that you will have the same level of performance. Okay? Nevertheless, this unsustainable approach that we have leads to very different forms of performance. So here is a building where you had a fire that progressed over 4 floors with very little structural damage. Here you have another building that actually had a fire that progressed on 10 floors, with very little structural damage. Here you have a building that was under construction, where effectively they had not put the fireproofing. In other words, it was not protected. Nevertheless, the building managed to withstand a very, very significant fire. In the meantime, You have similar buildings that have been designed under very similar rules, and then the result is total collapse. You might argue that this particular case was associated to the damage introduced by aircraft, but on the other hand, you have this one, which is the same vintage of building, which didn't have any damage, and only a few fires started in there, and the result is collapse. You can look at this concrete building, where the fire is actually a very, very small fire, so this is really not a very significant fire. Temperatures are probably extremely low. Nevertheless, the result is the collapse of the structure. Keep in mind that these three last buildings that I just explained were designed under exactly the same rules as the previous three buildings. In a similar manner, you can have cases where you have partial collapse. Again, same rules were used. Cases where you have full collapse. This is a Plasco building. And if I show you many of these fires, you can see different magnitudes of fires, different characteristics, completely different structural behaviors. Partial collapse, full collapse, no failure. So how come are we using the same rules and we're getting completely different answers? Is that a very common practice in structural engineering, that you actually design a building on the basis of your rules, and then every time that you test the building, you get a different answer? Clearly, that is not the case. So obviously, we need to look at the problem in a different way. Now, if you really want to do a sustainable approach, you have to do this with explicit performance. And explicit performance requires the understanding of materials, requires understanding how they burn. They require understanding how the heat and smoke gets produced, and how that heat and smoke gets transferred to the structure. So that then you can do a proper structural analysis, and the structural analysis can effectively allow you to deal with the issue of life safety, and effectively come up with an appropriate design that eventually will result in improvement of our codes or standards. This is what a sustainable approach is, okay? Now, if you go back and say, well, let's just think of how structural engineers think when they design a building, I took this from Buchanan, and you can see it's a very simple process, no? So you establish the functional requirements of a building, you make a conceptual design, you assume the size of the main structural members, and then you validate that your design is appropriate. If it's not, you iterate until you get the answer right. So it all starts by defining what the loads are. So we are all familiar with this type of concepts where you have a particular load, you have a particular design, and in the overlap, you will establish what is the probability of failure. We've all done that, and that's a very probabilistic approach, towards this issue, because the load is never the same load, so we have to have a probabilistic distribution for the load. Material properties, structural behavior vary within a certain range, some standard deviation, so we have a probabilistic distribution of the behavior. And we try to keep the capacity of the building very far away, from the loads that we have, but that overlap is an acceptable probability of failure. Okay? You can say 10 minus 6, 10 to the minus 9, depending on what building you have, but that's effectively what it is. So the first question that we need to ask is that if we're going to apply structural engineering principles, the first thing that we need to try to understand is what is the fire load. Okay, and this is the first place, where structural engineers stumble, because there is no such a thing as a fire load. Now, why there is no such a thing as a fire load? Because of thermal expansion. So we all know the concept that if you increase the temperature of a solid, it will expand, okay? And the problem is that if you leave, that structural element unrestrained, then it will not create a load. It will just simply expand unrestrained. The problem is that if we restrain the structural element, as we always do, the expansion creates the load itself. Now, this is not an imposed load that you can describe with a probabilistic distribution. It is a load that depends on your design decisions. So if you design to restrain things by using certain types of connections, you will get a completely different output. If you have a different beam, you will get a different output. If you change the materials, you will get a different output. If you change the geometry of the building, and therefore you change the fire, you actually get a different output. So you cannot impose the load. The load is actually the solution to the analysis. And that goes against the very intrinsic design principles that structural engineers use. So we can make the problem a bit more complicated and take into account all the things that matter. So if you look at the diagram on the top right, you will see that effectively the actual expansion is determined by a combination of two factors. One factor is the actual linear thermal expansion, where you increase the temperature and you have expansion of the material, and the other factor is the contraction that is associated to curvature. So if you get temperature gradients, those temperature gradients are going to result in thermal curvature, and that thermal curvature is driven by the temperature gradient, which is a thermal conductivity multiplied by the gradient of temperature as a function of depth. Okay? Now, once you subtract the compression from the expansion, you get the ultimate strain that is being created by temperature. And that strain can be described as a function of the thermal gradient and of the temperature, average temperature of the material. And for example, in this case, Usmani came up with a series of formulations that allows you to explain the problem. So actually, the fire provides two things. It provides the temperature, but it also provides the gradient. And if we don't take the two into account, we will never be able to establish what are the loads that are being generated. Now, people will argue that maybe this is not important, but unfortunately it is, because unfortunately thermally induced stresses are much, much greater than load-induced stresses in the case of fire. So failure is actually prompted more by thermal expansion than by actually the deterioration of the materials. Now, if I look at this problem then, is there such a thing as a fire load? There is no such a thing as a fire load. As a temperature and temperature gradient change, the load is going to evolve. And therefore it depends on thermal expansion and gradients. The way in which the load evolves depends on the characteristics of the design. So the different designs that I make will result in different formation of loads. And those are depending on restraint and on thermal gradients, on the fire and on the structural design. So a probabilistic distribution of the load is not possible. So extrapolating probabilistic methods of structural design into fire safety design, it is actually not an appropriate path. It actually will never work because it will never take into account the fact that you are creating the loads intrinsic to your design choices. So any fire-induced load has effectively a probability of 0 because any combination that I change will change the load. So there is no probability when it comes to defining what is a fire load. Now, then we say, well, then we have the material properties. And we know, we have a list of all the material properties that are going to affect the behavior of a structure. The Young's modulus of elasticity, plastic yield stresses, all these different things that you're very familiar with. And they all change in temperature, and we need to take that into account. And we've done that for many years, and you will find diagrams like this in the Eurocodes, in any national codes, where you show the evolution of these properties as a function of temperature. Okay? The question is, how are these temperatures or these properties obtained? We recognize that because there are material properties, and this is a very appropriate thing to do, we have to make sure that the material that we're testing is homogeneous in temperature. So we heat very, very, very slowly, so that we allow the whole material to be at the same temperature. Now, the moment that you allow the whole material at the same temperature, for example, when you exceed 100 degrees, that basically means that your material is dry. You've lost all the water, and effectively you have a dry material. So the properties that you are presenting do not include any effects of moisture. Now, is that realistic when you're dealing with fires? With fires, you have temperature gradients that are very high, that lead to heat fluxes of the order of 100 kilowatts per meter square. Those are very, very, very steep temperature gradients. Now, the heating period is extremely short, it's a few minutes. So that relaxation period that you use for your test, that is very appropriate to get dry material properties, is actually very inconsistent with the behavior that you experience in a fire, where you're going to have a rapid heating with massive temperature gradients. So effectively what you get is that if you heat with those temperatures, you can see in the dotted line in the plot, and this belongs to the group of Dr. Window here at UQ, where they've been doing absolutely exceptional work trying to look into this effect of temperature gradients in a systematic way. And you can see there's several hundred degrees difference between the core and the external part. So the water migrates to the inside of the material and accumulates at the heart of the sample.
So effectively what you're doing is when you look at a sample like the one that you have in the diagram and you expose it to a very high heat flux, what you get is a continuum variation of the materials. So it's like having layers and layers and layers of different materials, because we all know that the water content defines in many ways many of the properties of concrete. So instead of getting an homogeneous material with a single set of properties, what you have is like an onion with shells with completely different mechanical properties. Now, if you want to be able to model the fire, it is not appropriate to use an average temperature and thus an average set of properties to try to model properties that are changing drastically between the center of the sample and the external part. Because keep in mind that as the properties change drastic, the load within the sample gets redistributed, and you're going to have effectively different differential loadings in all the layers, which can introduce microcracking, all sorts of different things that will alter the mechanical properties of the material. So we have to consider all those things if we want to model fire. Now, furthermore, in some cases, we actually have made an effort. So, for example, when we're trying to define the total thermal strain, and this is again work by Lee, which is part of Dr. Dao's group, effectively, if you look at this, we have split the strain into the mechanical strain, the thermal strain, and we realize very rapidly that if we test it under load, it doesn't work. Why? Because if we only have thermal stresses and mechanical stresses, we're missing the combination of the two. Okay? So as good engineers, what we do is we add an extra term as a correction. Okay? So effectively, we correct the term by adding a third term that will serve to fix it. And when you look at the plot to the right, you will see many empirical correlations for that correction have been developed in the last 50 years. And we managed to fit to hundreds and hundreds of experiments this data to try to make sure that we corrected for the error. Now, let me ask you a question. When you set up a physical model, okay, and that physical model is intended to represent a physical problem, and it gives you an error of 42%, are you going to treat that correction as a correction, or that basically means that you're missing something in your physical model? You cannot treat a correction as a correction, a 42% error. Okay, so if you stick to 11 a.m., you'll see Dr. Dao's student explain a physical model that takes into account. Now, if you look at the very basic solid mechanics equations, the problem is that structural engineers like to work with very small displacements. So work is neglectable. But in fire, you get very large displacements, which basically means that work absorbs a lot of energy. So if you start with equations that neglect work, you will clearly neglect 42% of your strain. Okay? That's the problem. So effectively, there are reasons why this is happening, and we need to be very careful that we address these problems, and we just not do it on an empirical fashion, because we're going to end up using an empirical correlation to correct for half of the value of the property. So, like this, I can keep going on and on, but I'll just take one last example, which is the use of the standard temperature time curve. Again, the idea is that I standardize the fire as if it was a thermal load, but the problem is that I standardize it as a function of temperature. Temperature is a scalar, while heat flux, or the heat going into a structure, is a vector. And of course, the moment that I simplify the problem and I convert a vector into a scalar, I am missing some of the information. And the problem is that when I miss part of the information, I might end up missing the critical part of the information. So if I reconvert the temperature into the vector, what I will see is that, for example, the standard temperature time curve effectively provides a load that is dependent on the material that I'm testing. So if I am testing steel, for example, you have a load that increases monotonically, as you can see from the blue curve. While if I'm testing, for example, an insulating material, like the red curve, what I have is a load that increases very rapidly, and then very suddenly it drops to zero. So how can I compare the behavior of two different materials if I am testing them against different loads? And the reason why I'm testing them against different loads is because I used an oversimplified scalar when I should be using a vector. And the moment that I miss that information, I'm literally creating a test that has different standards for different materials. Needless to say, today everybody's talking about tall timber buildings. If you actually test timber that actually combusts, timber is producing energy and delivering it to the furnace. So effectively you have a negative load, and that's what you see in the case of the yellow. You have to open the furnace to vent it a little bit because it's heating too fast because the timber is providing too much energy. So using a very simplified approach results in a problem where you're truly not delivering what you're looking for. So the question at the end, and I think the message that I want to give is, are we paying sufficient attention to what we're doing? So we're producing tons and tons and tons of papers of structural fire engineering. You know, we are beginning to introduce performance-based design and structural engineering worldwide. You know, we have developed new materials that we're introducing into construction, and we're stuck in our very, very simplistic methods that were originally stemming from an implicit approach to performance-based design. So effectively, I firmly believe that, you know, if we are going to liberalize this field and we're going to start to work in a way that we quantify the way in which we design for fire, we have to pay a little bit more attention, and I hope that the few examples that I have given you illustrate to what extent we are ignoring the physics and we are just simply relying on a mechanistic extrapolation of what we do for other fields. Thank you very much.
Well, as I mentioned to you, you're going to get treated to a fantastic lectures, and Jose have just opened our eyes to how difficult to account for fire and how the nuances of you know, even in testing and so on for materials for fire to get the properties of materials. So thank you so much, Jose. And before you go down to your seat, I would like, on behalf of the ESEC committee, we would like to present to you a very nice 20-year-old used wine.
Thank you.
Okay, so for our next plenary speaker, we have Professor